It's my great pleasure to have this opportunity to come over here for 3 months. I'm learning a lot about hail hazard estimation, and I really enjoy it. And I want to thank my hosting professor, Dr. Kunz. You put a lot of effort into hosting me, and I really appreciate that. And a lot of thanks to the International Office for providing this opportunity, and also thanks to Dr. Nippers, because I know without your signature, none of this will happen. So before I start, I just want to acknowledge the students in my group. Here is the list of undergraduate and graduate students who have contributed a lot to the work that I'm about to present. So today, I thought I could start with a very brief introduction. This includes a self-introduction and a brief introduction to machine learning. And then I'll talk a little bit about the machine learning applications. So we actually did quite a few different machine learning applications in my group, but I selected only 4 of them, mainly because they are very different problems. It's my humble hope that maybe by showing this variety of different applications, some of you can also get new ideas about how machine learning can help solving your own specific problems. And then I also want to talk about some other research projects going on in my group, and I'll wrap up with some potential collaboration opportunities, mostly for students and the researchers at KIT to visit Canada or McMaster. So I'll start with the introduction. This is my research group. For those who don't know where Hamilton is, McMaster is in Hamilton. Hamilton is very close to Toronto, 15 minutes away from Toronto by driving, which is the largest city in Canada. We're also very close to Niagara Falls, and we're by the Great Lakes. The city actually sits on the Niagara Escarpment, which means we have over 100 waterfalls across the city. So that's the group. In terms of research interest, we are modelers. So we model different kinds of environmental engineering systems. This means we model watershed level hydrological and water quality problems. We model, we do climate downscaling so that we can analyze the local impact on different systems. We also model wastewater treatment processes. And besides that, we use another category of modeling techniques, that's optimization, mainly to provide decision support. And based on all that, we also try to propose integrated approach for environmental risk analysis and management. So coming back to machine learning, I know many of you are very familiar with machine learning. In climate change and environmental modeling, we most often use this as an alternative of the traditional simulation models that we use. For example, if we are building a climate model, what we'll do is we'll build a model using different governing equations as mapping function for the input and output. And those equations are most often the differential equations based on the law of physics. And now after you build the mapping function, you can feed the model with input, with initial and boundary conditions. And then you can predict whatever climate variables that you are interested in. For climate change, on the other hand, for machine learning, on the other hand, it's very different. When we use machine learning for climate change and environmental modeling, oftentimes we just use one branch of machine learning, the supervised learning, for classification or regression problems. And the way we built the mapping function is purely based on data. That's the most significant difference. And there is another difference is that this time when it comes to the input data, you no longer limited to the initial and boundary conditions. You can actually include any data that's available and that's relevant. So that's the difference between the traditional, so to say, first principle or knowledge-based or process-based model versus machine learning model. So now with that in mind, I want to show you some of the applications we had in my group. The first application I want to show you is climate downscaling. This is a project that we started in 2016, 2014. The background story is that there is a number of RCM projections that just started to become available for the province of Ontario, but there is a lack of ensemble projections, and there is a lack of high resolution projections for Ontario. And back at that time, machine learning started to show a potential for climate downscaling. So we started the work with the hope that we can leverage machine learning and generate high resolution and reliable climate projections just for Ontario, and then later we can use it for local impact assessment. So with that in mind, our machine learning models were very straightforward for us to set up. We take all of the simulation results we can get from existing RCMs as our input, and the output would be station or high resolution temperature and precipitation results. We tried a lot of different machine learning algorithms. First, mainly because we had different temporal resolutions. We want to see what's the best algorithm that fits our problem, and also because we had a bit of problem trying to improve the accuracy of precipitation prediction. So we tried different algorithms. And we had 10 years of data, splitting it into 70% for training and 30% for testing. We have a lot of results, but what I wanted to show you here is, well, in engineering applications, we always need to spend a lot of time validating the results. So what we did is we validate the results across 12 stations and across about 7,000 grids across Ontario, and then we compared the R-square value, the RMSE, and what we've learned is that machine learning can really help us increase the prediction accuracy and help us integrate results from different RCMs. And then we also evaluate the spatial distribution of the arrows. For the outcomes, we generated a lot of projections, and I worked with colleagues to provide them with climate information so that, for example, they can evaluate urban mobility and under climate change. We have colleagues in structural engineering who were just about to evaluate the building energy consumption, so they need the temperature as the input for their estimation. We also worked with structural engineers who are evaluating the risk of highway bridge, because in Canada we use a lot of salt, which introduce chloride to the surface road. This is mainly to prevent the road surface from freezing during the winter. So we provide climate information for them so that they can further evaluate the hazard or the risks brought by climate change. The projections that we generated, we shared it through a database. I have to admit that I'm not very good at spreading the words about our projection. We only had one link in one paper about the projections that we've generated, but we got 500 downloads so far, so we're happy about that. And we also got some publications with that. This part of work, we sort of put a pause on it, mainly because we've ran into two challenges. The first one is we noticed that there is a huge difficulty when we're trying to use machine learning to predict the extreme values. So here is the example. We use the different algorithms for just one location to predict the temperature. So you can see this is observation versus prediction. Overall, it looks good, but if you look at the two ends over here, the prediction of extreme values is not really that good. We dipped into this problem a little bit. So we realized that because we take RCM simulations as our input, but the RCM ranges If you see the green bars over here, sometimes the observation falls within the ranges, sometimes it falls outside of the ranges. And in both cases, machine learning will need to learn how to differentiate these cases and then provide more reliable prediction that's close to the observation. This is very tricky for machine learning, and machine learning simply cannot do that. And that we believe that's the reason why we are having difficulties in predicting extreme values. The second difficulty we've been having is it cannot really well reproduce the variability. So here is an example, temperature throughout the year. You can see the red is the observation, the fluctuation is always there. But if you use machine learning, try to predict the daily temperature, it always tends to predict the sort of like average the value. This is because the cost function in machine learning is to minimize the sum of errors. By predicting like a mean value, sort of average value, we can best minimize the sum of errors. And that's become a problem if you want to capture the variability of temperature. So what we are trying to do to address that is we turned over to bias correction. We try to improve existing bias correction methods because after all, our goal is to get reliable climate projection for impact assessment. That work is still ongoing. We were able to publish one paper about this, and down the road, we are hoping that we can sort of integrate bias correction and machine learning to further improve the accuracy. So that's the first application, climate downscaling. I don't know whether we should leave all the questions towards the end or I can. So please feel free to stop me whenever you have a question. So now I'm going to move on to the next application, which is hydrological forecasting. We actually did a few different things with hydrological forecasting. We used machine learning alone for hydrological forecasting. We've built models, hybrid models based on physically based hydrological model and machine learning. But today, what I want to present is something that's different, something that's not directly for stream flow forecasting, but we use machine learning for estimating the parameter uncertainties. So the background story is not just for hydrological models. For all types of model, we have a lot of parameter uncertainty. So to quantify the uncertainty of the parameters, what we usually do is we can take the range of the parameters and then sample different values from that range, run the model over and over and again. If you run it enough times, you'll have different samples for the output, and those samples can be good enough for you to generate a distribution for your output. So this way you can turn the distribution of your input, your parameter values into the distribution of your output. This method is actually very robust. You'll be able to get very robust results, but the problem is it's very time consuming. So what we did is we turned over to a more efficient methods called polynomial chaos expansion. This is for estimating how the parameter uncertainty can be translated into the distribution of the output. So the PCE methods, the idea is that instead of running the model over and over again, get enough sample to build the distribution for the output, we now use just one equation to represent the distribution in the output at any time step. So the equation here, the that you can see here, they are all standard normal distribution. So now you're representing the distribution of your output using combination of standard normal distributions. So this is why the method is very, very efficient. You don't need a lot of samples. All you need to do is to determine how many standard normal distribution you want to use, and then determine all these coefficients, and then you can describe the distribution of your output. So now the problem becomes estimating the coefficients. So what we can use is a method called probabilistic collocation. This means if you have the input, historical output, then you can use this method to estimate the coefficient. Once you have the coefficient for every single time step in your output, you can use an equation like this to represent the uncertainty caused by parameter uncertainty. So this looks very nice, it's very efficient, but the only problem is if we want to use this for forecasting, it's almost impossible because we won't have the future flow. So the solution that we came up with is we introduced the ANN, machine learning, into the whole uncertainty quantification process. Conventionally, you will have to actually get the flow value before you can estimate the coefficient and use the PCE method. But now, if you use ANN, you don't need future flow anymore. We can build a relationship between the coefficients and the historical input data, such as temperature, precipitation, wind, humidity. So that's what we did. We used the ANN to build the relationship. Here are some, and then once the model is built, we used it for a semi-distributed hydrological model. We selected a watershed in the States, and then we built our PCE model, and then we used the ANN to estimate the coefficients. So the idea is now that with PCE, we just need to run the model for 243 times, then we can quantify the uncertainty in the output, which is caused by 5 uncertain parameters. Whereas if we use traditional Monte Carlo simulation, the baseline simulation that we did, we used the 10,000 iterations. So the result was actually quite good, especially for the historical period where we used only 200 simulations to completely reproduce the uncertainty analysis result from 10,000 Monte Carlo simulations. And when it comes to forecasting, the forecasting of the mean value of the probabilistic forecast, we captured it very well. But it comes to the standard deviation, it's not that good. But if you look at the time series results, we were able to capture all the peaks. So we were quite happy with this. To summarize, this was the first time we used the PCE for this kind of uncertainty analysis. And because of machine learning, we now enabled PCE to provide probabilistic forecasts. So based on that, we extended our work to some other problems because this can be used not just for hydrological modeling, but also for other applications. We used it for wastewater modeling system, and we further improved the algorithm so that we can further address the interaction among different uncertain parameters. So that's the second application. The third one is for river flow event prediction. This is relatively new. The background is that in Canada, an yearly event on our river is that in the springtime every year, the river ice will slowly break up. And sometimes when the breakup causes a damming effect, then that could be catastrophic because if there is a damming effect, you got a lot of ice chunks on the river, it can cause a lot of flooding. It usually carries the highest flow rate and the highest water level throughout the year. So that's something we want to prevent. But now with climate change, we don't see that only at the springtime, we see it multiple times, even during the middle of the winter. So that's the problem. We don't want to see this. We want to know how often we can expect this under climate change. But midwinter breakups is very difficult to simulate. Currently, we don't have any process-based model that can well simulate midwinter breakups. So what we came up with is we worked with Environment Canada. We got a nationwide river ice database from them. So you can see this is the distribution of the river ice data sets. The red ones are the ones that had experienced midwinter breakups. We got a lot of data and we tried to predict when the midwinter breakup is going to happen. So we developed this two-level modeling system, mainly because throughout the whole winter, we won't be able to predict specifically one day, day by day. It can be very computationally expensive. So we divided this into two levels. First of all, we looked at certain periods. Say, if, for example, in these 2 weeks, midwinter breakup is going to happen or not. If yes, we move on to the second level and then use binary prediction to see if it's going to happen within the next 3 days. 3 days is good enough for the downstream to prepare for the ice breakup and to do evacuation if it's needed. So the model that we built, because this is binary classification, we used some different metrics. We had 80 to 20 split of the data. And then here are some deterministic results. We got very good prediction accuracy. Environment Canada were very happy about this. We tried 4 different algorithms. Turned out that there were 2 that consistently performed very well. And we proved that the two-level structure worked really well. On one hand, it can save us a lot of time. On the other hand, it can provide rather decent accuracy. And on top of that, we also try to provide probabilistic prediction from the model. This is only for the second level. We can get same result from the first level. The probabilistic prediction can still have a bit of room for improvement, but right now, we consider this as a second source of decision support. Having some probabilistic information can be quite handy. It's just the methods itself. Maybe we still need to further improve that. So you can see that for these evaluation values, we want them to be as close as to 0. Sometimes it's good, but sometimes it's not as good. So to sum up, this was the first study that's based on machine learning, and that's for cross-country midwinter breakup prediction. And something that so one thing that I want to point out is our prediction relies only on climate data and the freezing data at the beginning of the season. So in the future, if we have climate projections, we can very easily modify the model to provide some sort of long-term prediction. So to extend this work, we actually have been improving the algorithm. One thing that I would like to point out is we introduced an ontology-based methods. These methods can help us deal with some data that's not really quantitative, it's qualitative, and that's collected from, say, experts instead of sensors. So this is something that we are still working on, and we hope that once we develop this hybrid framework, it can be used not just for midwinter breakup prediction, it can be used for other things as well. So moving on to the last application, this is for wastewater modeling, a totally different system. We started with a software simulation company. They are the top one in North America, and I believe they also have customers in UK. Germany, I'm not sure, but the customers are municipal wastewater treatment plants. So this software company, they've been working in simulating every single process that takes place in wastewater treatment plants. So they have sophisticated models to simulate what's going on while our wastewater is being treated. However, what they have no idea about is how much and what's the quality of water that's coming into their wastewater treatment plant. The problem is more complicated because everything relates to when people get up to take a shower, or if there is a precipitation event or not. So we took it over, we developed a machine learning model for them to predict what's coming into the plant. So the mapping function here is machine learning. We used different things to represent the pattern that could affect wastewater influence. And the goal is to predict the quality and amount of water coming into wastewater treatment plants. So they were happy about this. I think our product have been integrated into their commercial software, and now it's being used by dozens of municipal wastewater treatment plants in the States and in Canada. One in UK, but I don't know the rest about Europe. And then because of that, we got approached by more industrial partners. They want to see more applications of machine learning. One example here is we use membrane to treat our wastewater. So membrane, you can consider this as a filter. When you have wastewater flowing through the filter, the waste will accumulate on one side of the membrane. If you have a lot of accumulation, it's not a good thing. You won't be able to treat a lot of water. The flow will decrease significantly, and also the treatment performance will decrease. So this means every once in a while, you need to backwash the membrane to clean the membrane using chemicals, or you even need to shut down a unit and then clean it manually. But the more frequently that you clean it, the more cost that would bring. So they want to predict when fouling is going to happen. So that's what we did. We developed a model to help them using their sensor data, which is every 50 minutes, they got hundreds of data points monitoring different parameters during the process. And then we developed a model to help them predict this. Again, this is a process where we don't have any existing model to simulate. So this is where machine learning comes in handy. So that's all the machine learning applications I want to cover for today. Moving on, I want to talk about some other research projects going on in my group. Aside from machine learning, we also work on process-based models. And sometimes if either works very well, we consider integrating them, design an integration framework simply just to improve the accuracy. We've been working with the indigenous communities in Canada to help them improve their water security. You see, that's me here in the middle of the pandemic, and I was, I think, 5 months pregnant, and so I was wearing the mask. Very careful about everything, but we installed the water sensors in their community. We built a database for them, for the community to check real-time water quality from the sensors. And another thing that that's ongoing is we're trying to build digital twin models for infrastructure networks under climate change. We look at, because I'm from civil engineering, we have colleagues from transportation, from highway, from me, myself, we work with water infrastructure. So we want to see the interaction of this infrastructure under climate change. So that's another work that's going on. And another machine learning application has something to do with nuclear waste. So we still have nuclear power generation going on in Canada. I know it's shut down in Germany now, but in Canada, we generate a lot of low-level waste. By low-level waste, it means the radiation level is really low. For example, if you go into a plant, you need to wear a shoe cover. If you clean a place, you need to wear gloves. All those things are considered as low-level waste. And over the past 30 years, we accumulated a lot of waste, and there is now a problem of storage. So they wanted to sort of sort all this low waste and see if they can recycle some of it. But this whole process is now done manually, which is very costly, very time consuming. So what we are trying to do is trying to develop a system so that they can rip open a bag, take a picture, and then use image processing to recognize what's what in the bag and help them automate the process. And we're also working on another, this is very new, we just got the money last month. just to map the energy consumption from different buildings so that we can do a little bit of optimization with the heat storage, because heat is the main source of for energy consumption and also green gas emission in Canada. So that's what I want to cover, because I know this is outside of meteorology or atmospheric research, so I left a lot of technical details outside. Like I said, I was just hoping I can show you all different kinds of problems that machine learning can help solve. So now I want to wrap up with some potential collaboration opportunities. We have the MITEX, which is a funding agency in Canada. They have a special call just for students in KIT. So if any full-time graduate and undergraduate students are interested in coming to Canada to work on a research project, they can get sort of funding from MITEX. There is also the Ontario Baden-Württemberg exchange program. This is mostly for postdocs or junior professors or researchers. If they want to come to Canada, they can get a little bit of support from this program to do some sort of exchange, just as what I'm doing here. And we also have from the university level small seed funds to support the collaboration between McMaster and any international collaborators from outside of Canada. And then there is also opportunity from DFG, but that I'm not quite, I don't have a lot of information. I got this from Oliver from the international office. I just thought I should mention this just in case someone would be interested. So that's everything. Thank you very much for listening. Thank you.